Okay, good. So Taoufiq, Damir will be speaking on physical layer communications, lattices, and number theory. So please.
Okay, thanks, Frank, for the introduction. I'm really pleased and honored by such an invitation. So today I'll be talking about physical layer communications, lattices, and number theory. I'll firstly introduce some basics of communications and then try to build from scratch some problems and translate them to lattice language, and then possibly propose some solutions in the number theoretic framework. So the context here is communication. So when we talk about communications or communication problems, we mean basically two types of problems. The reliability, which is a reliable communication, is basically a communication that ensures that the message reaches its destination incorrupted and complete. And that's classically approached by coding theory. And the second requirement is security. And you all know that we classically approach this problem by cryptography. But today I'll be talking about something slightly different, physical layer communication. So before digging into details, let's look at what happens when we communicate. So on the left, that's me on my computer trying to communicate with probably one device or multiple devices in the East Coast of the US. So before that the information leaves or quit my device, it passes through 7 layers. So the first layer is defined by the human interaction with the machine. In my case, I'm using Zoom. So it could be a browser, etc. So that's where we deal with applications. And then my voice or a picture will go to the 6th layer, where this is where the data is converted to symbols, basically. And that's where we crypt also the data. That's where cryptography happens. And we have these 3 layers that plays kind of the role of the post office, where the information is organized into packages and etc. But more importantly, we have this second layer where we basically correct errors. So in this layer, we equip our data with some smart coding. So later the receiver will be able to detect and correct the errors. And the bottom layer, which is the physical layer, that's where the information is sent in a physical form, like a wave or a signal in the case of wireless communication, or a voltage. So I'll be mainly interested in this physical layer. So as you can see, cryptography and coding theory sometimes ignores the characteristics of the noise in the channel. So physical layer communications is simply this science of improving reliability and security by using our understanding of the noise. And we can, by this, I mean, modeling the channel, by studying channel models. So here is an example of a channel model. This is a SISO channel, single input, single output. This means that we have a single transmitter and a single receiver. So the transmitter will send a message X, and this message, something will happen to this X in the way, so the receiver will receive a corrupt version of this X, it's Y. And this is in general modeled in this way. So thanks to Shannon and others, we can represent signals of finite bandwidth as points in Euclidean space. So in my context here, the message will be just an element in a finite subset in Rn. And the channel model, or this noise, it's kind of, the noise can be generated by different means. So it can come from different sources, from the heat generated by my machine to the atomic interactions between atoms. And so it's kind of hard to model it as a deterministic model. So we have a probabilistic model. And we can, this fade-in SISO channel is modeled as X, and we will have a diagonal matrix that will distort the coordinates of X. And this diagonal matrix is filled with some random variables. And also we can assume that the nature will add some noise, random additive white Gaussian noise with some variance. So how do we correct errors? Here we have a code book, which is just this discrete points inside this green ellipse, and we send X, and the receiver receives this Y. So assuming this extra assumption that the receiver can measure this H, correcting the error will be, we will use a maximum likelihood decoder. So the receiver will just try to find the closest point to the received point inside this code. And the reliability of this code will be measured by the so-called point-wise error probability. This is just the probability of the received point being closer to another point other than the transmit point. And a trivial solution to avoid or to minimize this probability of making errors is by choosing the code to have such that the distance between any 2 points is large, so that this decoder will not confuse this X with X prime, because X prime will be so far. But this is not a practical solution, because the transmission power in general is measured by the Euclidean distance of the point. So this trivial solution will require a huge amount of energy, and we don't want that our devices dies after a few seconds of communication. So we kind of want to design this codes such that they are packed, but with some reasonable distance between the points. So we can reformulate our reliable codes design criterion as given a channel model and a fixed transmission power. We want to construct these discrete subsets of Rn such that the probability of making errors is as minimal as possible. So our goal is to design these discrete subsets. But we will ask an extra requirement for this discrete subset. We want them to also form an additive subgroup of Rn, so to be able to do some algebra later. And I'd call a lattice just a discrete additive subgroup of Rn. And actually, any additive subgroup of Rn is discrete if and only if it is a z-linear combination of some real vectors. These vectors are called the basis of the lattice, and the volume of the lattice is just the determinant of this matrix. And here I'm considering the vectors to be column vectors. And also any change of basis will generate the same lattice. And you remember my transmission power requirements. So we want also, we can assume that the volume, all these lattices, that to compare fairly lattices in this communication setting, we want them to have the same volume. So we'll assume that they all have volume 1. So this is kind of equivalent to a fixed maximal transmission power. And as I said, lattices can be described by this, or full rank lattices can be described by this matrices of determinant plus or minus 1, that's volume 1 lattices. And we can identify the space of lattices with this matrices modulo change of basis. And this is of dimension n square minus 1. And again, we can reformulate our design criterion as given a channel model, find a lattice such that the probability, such that the union of point-wise error probabilities is as minimal as possible. So we can later carve from these lattices a finite code book by choosing these points of minimum that allow us to reach minimal error probability. Okay, so this is a problem on the space of lattices. So in general, thanks to this matrix representation of lattices, many lattice problems can be solved by means of linear algebra. But actually, the lattice problems becomes more interesting when we see lattices as metrized objects. So sometimes lattices are defined as an algebraic structure with a metric or with a form. So the classical metric to consider in lattices is the Euclidean distance. And we defined, with respect to the Euclidean distance, the shortest vector length in L to be lambda 1. That's just the length of, or square length of the shortest vector, and S of L, the set of shortest vectors. Now let's go back to our channel model. Remember, we have this SISO channel model. We send X, we have random H and random noise. Now, assume that this H is just the identity. So we recover the so-called the additive wide Gaussian noise model, the AWGN model. That's we send X, and nature, say, adds just a random Gaussian noise. And this pointwise error probability is bounded, upper bounded by this function. So this is the complementary error function. What we need to know is that it's a decreasing function on the positives. So a strategy to minimize this probability is to pick a lattice that minimizes this probability is to pick a lattice with a high shortest vector length. And I think that reminds you of a famous problem. It's the sphere packing problem. So minimizing, that's the problem asking for finding a lattice, say, of fixed volume with the longest shortest vector. So this is a kind of hard problem. It has a long history. So for example, just this problem in dimension 3, in its full generality, took humanity like almost 400 years, from Kepler to Hall, 1998. So here we want a quick solution. We want to find these lattices. But a good strategy when we deal in general with optimization problem is to restrict them to a smaller, see if we can restrict them, or if we can find this optima in a smaller set, or because this ln is quite complicated and big. But in general, when we deal with the Euclidean distance, it's kind of handy to look at lattices modulo rotation, because the shortest vector or the Euclidean distance is invariant under rotation. So it's logic to look for this sphere packing or best sphere packing lattices modulo in the space of lattices modulo rotations. And in the case of planar lattices, that's how it looks like. This is the Poincaré upper half plan. This kind of half the fundamental domain. So S2, the space of similarity classes of planar lattices, is this gray tube. Now remember, we restricted our sphere packing problem to this tube. So can we do better? Can we restrict it to a smaller, even smaller space? And yes. And this leads me to the next definition. So a lattice will be well-rounded if the set of shortest, the span of R of the set of shortest vector is the whole space. And the space of well-rounded lattices are denoted by WN. And this property of having, say, n independent vectors inside the shortest vectors is invariant under rotation. So it's also natural to consider these similarity classes of well-rounded lattices. And again, for the two-dimensional case, this well-rounded lattice is just this blue arc here. And yes, we can restrict this sphere packing problem to this blue arc without loss of generality, thanks to a theorem of Voronoi. Actually, what I meant by a small, the well-rounded locus is small, is actually we can equip the space of lattices with so-called Haar measure, and this space is of vanishing measure. And it has also this nice property, it is also compact. And you know, it's always nice to restrict our optimization problems to compact sets. So what we did so far, we start with a channel model, the AWGN. We formulated the reliability problem as an optimization problem on the space of lattices. And we found that it's kind of equivalent to this hard problem on lattices. And we restrict, so one natural direction to take is to restrict it to a smaller compact subsets. So probably we can find some other alternative solutions. Okay, so we talked about this AWGN channel and how we connected to the sphere packing problem and how we restricted this problem to a smaller space. And this is also, and also we talked about the AWGN channel. It requires, or for building good codes for this AWGN channel, we want these lattices. And that was in the Euclidean geometry, say, framework. We can also define another, say, norm by abuse of terminology. I call it the algebraic norm. So for a point in the lattice, I call the product distance just the product of coordinates. It's not a norm. It's not a distance. Actually, we don't have even this least requirement that norm of x is 0 if and only if x is 0. It's enough that one coordinate is 0, then this norm will be 0. But lattices satisfying this condition, norm of x is non-zero for all non-zero x in L, we call them full diversity lattices, and we'll need them in Y. And to mimic the short vector or shortest length definition, we define the minimum product distance by just the minimum of this norm when x is non-zero in L. Now, back again to our channel model. This time, earlier we considered this H to be the identity. Now we consider it to be just a diagonal matrix filled with random variables following the Rayleigh distribution. And this model is kind of realistic when we communicate in densely built cities, for example. So that's my East Coast element in my presentation. Manhattan has been shown to approach this model. And let's see how we can improve reliability of communication in Manhattan. Okay, so considering L to be a full diversity lattice, that's a lattice with non-vanishing minimum product distance, the pairwise error probability is upper bounded by this quantity. So this sigma is the variance of the noise, but more importantly, we have in the denominator this quantity. So to build reliable lattice codes in this relay fed-in channel model, we want L that maximizing this minimum product distance. Okay, and another thing to mention is that this norm is, or this product distance is preserved by the action of the diagonal group, which has just the diagonal matrices with positive entries and determinant 1. Okay, so we defined so far 2 channel models, so the Gaussian and the fade-in. So to resist the Gaussian noise, we want good sphere packing, and these sphere packings are inside the well-rounded locus. To resist fade-in, we want lattices with high product distance. And what about if we want both, resist Gaussian noise and fade-in? And this is realistic sometimes in, to give you an example, when we need these two properties to be satisfied, is when we communicate in a densely built city that's defined by fade-in, and in the same time we communicate with the satellite, where in general the channel is modeled as a Gaussian channel. So we want to satisfy both. But there is no obvious trade-off between these two properties, because this product norm, algebraic norm, and the Euclidean distance define 2 different geometries, say, on the lattices. So we have 2 possible strategies. So either get the best sphere packing lattice and act by rotation, and the rotation will not change this property, but find in this orbit of the action of rotation on this lattice, the lattice that have the largest product distance. And or find the lattice that maximize this product distance, and that is also a full diversity, and act by the diagonal group, and this also will not change this property, and find in this orbit the lattice with largest sphere packing radius. So as I said, it's kind of hard to find those, and this problem is not even convex even in the 2 dimensions. So we'll adopt the second strategy. So we'll try to find these full diversity lattices with high product distance and act on them by the diagonal group, and look in this orbit for the largest sphere packing radiuses. So we want to construct first full diversity lattices, and among them try to find the ones with, say, good minimum product distance, and in this orbit find the largest sphere packing. But instead of looking in, because this largest sphere packing or this local maxima of the sphere packing lives in this well-rounded locus, we can formulate our problem in the following way. Taking L to be full diversity lattice, can we explicitly describe this intersection between the action of the diagonal group and the well-rounded locus? Now, the first question or natural question that one can ask is this intersection always, do we have elements in this intersection? Is it empty or not? And thanks to the theorem of Solin, yes, it's not empty. There is always an element in this intersection. You take any lattice, you act by diagonal matrices, there will be at least a well-rounded lattice there. And we can also restrict maximizing the product distance to maximizing this product distance to this well-rounded locus without loss of generality by a direct application of this theorem. Now, what we have seen, we formulated this simultaneous goodness in the Gaussian and fading environments to finding full diversity lattices and that have a maximal product distance, and acting on them by diagonal matrices and finding the intersection of this orbit with the well-rounded locus. But we use mostly topological methods here, use some dynamical methods, but we need to construct them explicitly. All what I said are existence results, but we need to answer this engineering requirement. Existence results are not enough. We want to explicitly construct these lattices. And I think Padma announced the math meme context, so that's my input to the math meme context. Okay, so to construct these lattices, we will use the rich arithmetic structure of number fields. So I use the standard notations. So K will be a number field of degree n, R1 the number of real embeddings, and R2 the number of complex embeddings. OK is the ring of integers, sigma 1 to sigma n, the n embeddings of K into C. I'll use the norm and trace usual notations, but more importantly, I will be interested in studying the canonical embedding from K to Rn. So taking an element in the number field, I'll just send it to the first real embeddings and then split the complex embeddings to real and imaginary. Because we have 2R of them, this vector will be of length n. So this is an embedding from K, the number field, to Rn. And for any ideal, actually any order in the ring of integers, the ideal sent by this psi will be a lattice. And if the field is of degree n, this lattice also will be of rank n. Its volume also will be the norm of the ideal times the square root of the discriminant. And in the case of real number fields, any elements in the field is sent to the n embeddings or real embeddings. So consequently, the Euclidean norm will be connected with the trace, and this, what I call the product distance, is equal basically to the norm of this T. And thanks to this basic property of the norm, so the norm of T will be 0 if and only if T is 0. So all the lattices constructed from totally real number fields have this first property. So we get it for free. And basically studying the Euclidean norm and the product distance on these lattices from number fields leads us to study the trace form and the norm in the number field. And what I call the minimum product distance of the lattice rising from a given ideal in a real number field will be the volume of the lattice over the discriminant times this minimum, where T is ranging over the ideal. And if I is principal, and you remember that we want that our lattices are of volume 1, so this normalizing this lattice is to have volume 1, the product distance of a lattice arising from a real, from an ideal in a totally real number field is simply 1 over the square root of the discriminant. And you remember for these fading channels, we want lattices that are full diverse. So any lattice arising from a real number field, totally real number field, will have this property for free. And we have a kind of recipe to construct those that have high product distance. It's basically those arising from ideals in real number fields of minimal discriminant. So we started with the fading, the so-called Rayleigh fading channel. We want to construct full diversity lattices with high product distance. So a recipe to construct these lattices is to find real number fields of minimal discriminant. And this is also a long-standing problem in number theory. Okay, so as I just showed, if L is arising from a real number field, then L is a full diversity lattice. And that's exactly the lattices we want for this Rayleigh fading channel. And actually the converse is conjectured to be true. Margulies conjecture that this full diversity lattices for higher dimensions, dimensions greater than 3, are necessarily arising from real number fields. So assuming Margulies conjecture, the only way to construct these lattices, or there is always a way to construct these lattices from real number fields. So to formulate our problem, the number theoretic framework is the right framework for constructing these good lattices for a Rayleigh fading channel. Okay, so now, if you remember, my strategy is constructing this good, we want this full diversity lattices, and we act on them by the action of the diagonal group, and we want to look for high sphere packings in these orbits. Basically, study first the intersection with the well-rounded lattices, and then look at this, choose the one with highest packing density. So in a joint work with David Karpuk, we attacked this problem for quadratic number fields, and we started asking all kinds of questions. So for example, given an ideal in quadratic number fields, we produce an algorithm given all the elements in this intersection. We produce a counting estimate of the number of elements in this intersection, and it was in terms of the regulator and the discriminant. We classified some of this element when this intersection contains just one element, and we produce infinitely many of them, and this involves the negative Bell equation. Also proved that taking I, or the ideal, to be the full ring of integers in cube square root of 5, that's basically the highest possible product distance among all quadratic ideals, produced infinite families with good sphere packing and high product distance, and that was from Markov numbers and Fibonacci numbers. So if So this is just to illustrate that even like starting from a purely engineering problem, we can end up doing all the fun number theory, or all the number theory we like. So in another joint work with Lenny Fukshansky, so instead of dealing with the action of the diagonal group, we considered the action of totally positive elements. And again, classified when these ideals, or when an element in this orbit of the action of this set contains well-rounded lattices. But that wasn't one example of linking this purely engineering questions to some, say, fun number theory questions. And that was in the context of reliable communication in the fading and Gaussian channel. Actually, we can, by studying also the noise in the channel, we can also improve security. And that's what we call the wiretap channel. So the wiretap channel is basically a method that uses our understanding of the noise to kind of hide the message. So there is no encryption involved here. So we use just the nature noise to hide the message. We need just one assumption to assume. For example, if we use Apple Pay or Google Pay or our chip in the card, so we approach our card to the machine. So we assume that the signal here is stronger than the eavesdropper signal here. So the only assumption we assume here is that the signal quality in the eavesdropper channel is weaker than the one between the legal transmitter and receiver. And just by assuming this assumption, one can build a smart coding method to confuse this eavesdropper. And again, the security here is measured by, because here we have two channel models with just the noise in this channel is greater than the noise in this channel. And we can measure the security by the probability of Eve correctly decoding the message. So we want, again, to minimize this probability. There are other measures based on information theory, etc. But just to stay consistent with what I said in the beginning, and a measure that one considers is the probability of the eavesdropper correcting correctly decoding the sent message. Unfortunately, I don't have time to explain this coding technique, but it's the so-called coset coding. So we here in this context, we choose a lattice and a sublattice. And the idea is to confuse Eve by mapping the information not to a single vector, but to a coset modulo some sublattice. So assuming that the Eve channel is degraded compared to the one used by the receiver, Eve will not be able to decode, but the receiver will be able to decode. So it's kind of a smart way to confuse the eavesdropper. But what I want to say here is just this probability of Eve correctly decoding the message is linked with the so-called flatness factor. So this is the volume of the lattice. This is the variance of the noise. And here we have this interesting object that you all know is the theta series of the lattice. That's just the sum over Q to the power the norms of elements in L. So using Poisson summation formula, this guy becomes the theta series over the dual lattice. So the dual lattice is just the elements in R with integer dot product for all Y in L. And the Eve's correct decoding probability is upper bounded by the index of this chosen sublattice inside the superlattice times this flatness factor that is defined by a theta series. So if in the reliability context, we ended up studying rings of ideals in real number fields, fields invariants, here we end up studying the theta series of lattices. And we can do a lot of things or use our knowledge of, say, modular forms or Epstein zeta function and so on to study these objects. So the goal here again is to minimize this quantity. So what we did is we analyzed these well-rounded lattices in the wiretap channels by analyzing, generating the noise, like by algorithms and generating noise, etc., and establish some mathematical links between well-rounded lattices and physical layer security to minimize this upper bound. And also in a joint work with Guillermo, we introduced a family of lattices with explicit well-rounded sublattices. So it has some applications in this context. But just to summarize, we start, so the general idea, or what I want really to highlight here, is that we start with the physical layer communication context. This belongs to the faculty of engineering or electric engineering and communication engineering. So in this framework, we study channel models, probabilities, reliability, security, assumption. We formalize our problems as optimization problems. So because we are in this wireless setting, we can represent the signals as points in Euclidean space. So the codes are discrete points in the Euclidean space. So we can, based on these assumptions and probabilities and optimization problems, we can translate these problems to lattice theory. So lattice theory, we can use in geometry, topology, and dynamics, for example, the action of groups on lattices, or topology to prove the existence of our optima, etc. But number theory is provide a strong tool to translate again this problem to an arithmetic context. So you remember we start with Rayleigh fed-in channel, Gaussian channel, wiretap channel, but we end up studying number fields invariant, like transform, discriminants, theta series, and so on. And this was just for this one channel model called the single input, single output. For example, there is this other model called MIMO model, multiple input, multiple output, where many transmitters are communicating with many receivers. And here the message is seen as a matrix rather than a vector. And the right framework there is the simple division algebra or central division algebra or quaternion algebras over number fields. So this physical layer communications provide a nice framework of collaborations between electric engineers, computer scientists, topologists, dynamics, and number theorists. Okay, so that's this topic. If you are interested in reading more about this topic, so this first book is about this algebraic coding in fade-in channels. Here we have like the famous book on lattices, sphere packing, lattices and groups by Conway and Sloan. And if you want to learn more about number fields and lattices, I recommend all the work of Eva Bayer. And if you are more interested in what I did in this direction, so that's a list of references also, and this too. Okay, that was roughly what I wanted to say. Thank you very much.
All right, thank you. That was fantastic. Questions for the speaker? So I have a question.
Yes. Should I stop sharing?
Please keep sharing, actually, because I have a question about
Yeah.
So you mentioned this rather amazing looking conjecture of Margulis, which I believe was for n at least 3, any full diversity lattice comes from a real number field.
Yep.
So I apologize. Could you remind me again what a full diversity lattice was, please?
So this is a lattice with the minimum product is non-zero. So all the coordinates are non-zero except 0. So the product of coordinates is always non-zero except for 0.
Okay, so I guess according to this conjecture then, so most lattices will not be full diversity lattices. Is this correct?
What do you mean by most lattices?
So for example, suppose you have some full diversity lattice and you take any basis for it. And suppose you were to shift each of the basis vectors by some random and extremely small amount.
Yes.
Then I guess you would not get a full diversity lattice. Is that right?
Yes.
Okay, and what would fail?
What would fail in what?
So my intuition is that this full diversity lattice should be kind of a Zariski open condition where most lattices satisfy it, but evidently my thought is wrong. So if you shift the generators a tiny bit, I guess, why is it not a full diversity lattice? What property will fit and how?
Because here I said that basically Margulis conjecture is about the product is strictly greater than 0.
So if you shift it a little bit, it'll become...
full diversity lattices are also from number fields. So Margulis conjecture is by saying the only way to avoid axes is by using algebraic constructions. And this is basically, this condition is equivalent that to the orbit is bounded. The orbit of the action of the diagonal group on the lattice is bounded. And not all the lattices have this property.
Okay. All right, thanks.
Yes, because I see your intuition, because Margulis, when he introduced this conjecture, was in the context of Littlewood conjecture, the product of you take 2 real numbers and n, alpha and beta, so the nearest integer to alpha times n times the nearest integer to beta times n outside, this limit m goes to 0. So kind of the same as your, and which I can explain if we have a blackboard.
Right.
But,
yeah.
So.
Okay. Any other questions? Okay. So let's thank our speaker again. And so just a couple of announcements. So at 2:40, we have another of these coffee breaks, but the format will be a little bit different. So there are 5 different rooms you could join. So please see the schedule, and there are Zoom links for each of them, hosted by different people. Otherwise, so the next talk will be in parallel sessions at 2:15. Okay, thank you.